Hello all, I'd like to thank organizers for giving me this opportunity to talk in this virtual SCONA conference. I'll be presenting some preliminary validation data for our open source complete airway CFD model. To model inhaled drug deposition throughout the tracheobronchial airways, our group has developed the stochastic individual pathway or SIP modeling approach over the last decade. In this approach, individual continuous pathways beyond the third bifurcation are generated extending into each lobe of the lung through the terminal bronchioles around bifurcation 15. A sufficient number of stochastically generated pathways are simulated until deposition results converge to an ensemble average. This approach is reported to reduce the required number of time to simulate the entire TB region by a factor of 10 to the power 5, with only an estimated minor loss in accuracy as reported in this paper. Previous studies have focused on finding out required number of SIP paths to resolve deposition and whether a fully transient simulation is needed. Further, our group also extended the SIP modeling approach to include entire lung by combining with a CFD models for SCONA region. Using this SCONA CFD model, correlations have been developed for slow and deep inhalation and quick and deep inhalation with breath hold. With the current study, we are focusing on implementing this complete airway model in OpenFOAM to make this model freely available to other researchers from industry and academia. Currently, the SIP model is implemented in commercial CFD code and is fluent with various in-house routines for model improvement. Therefore, the initial challenge is to benchmark the CFD methods in OpenFOAM and reproduce the published deposition results. Over the past year, we have been studying various Lagrangian solvers in OpenFOAM version 7 and characterized different solvers for our CFD needs. For example, we are using DPM foam for upper airway dry powder inhaler simulation, and we are using spray foam for upper airway meter dose inhaler simulations. Further, we have implemented new libraries for a low Reynolds number k-omega turbulence model and stochastic particle dispersion model with anisotropic near-wall turbulence correction. We have also updated particle injection methods and particle post-processing methods in OpenFOAM. We have tested the in-house implemented turbulence libraries with other available turbulence models in canonical geometries like vertical pipe or 90-degree band, and found that k-omega models, both SST and low Reynolds number k-omega model with anisotropic correction show very good agreement with experimental data for deposition in these geometries. For implementing preliminary complete airway model for DPA applications, we have developed an upper airway CFD model combining DPI mouthpiece with characteristics models for mouth throat and upper tracheobronchial airways up to third bifurcations. Previous studies have reported that one SIP pathway in the lower left lobe is representative of average lobar deposition. Therefore, we have implemented SIP pathways in the lower left lobe using two SIP models, one extending from bifurcation 4 to bifurcation 7 and another from bifurcation 8 to terminal bronchial bifurcation 15. Further, aerosol deposition correlations from previous study was combined with the SIP model. We have used flow rate outlet velocity boundary condition in the upper airway outlets to match the estimated ventilation to each lung lobe. Further, we have sampled the velocity and turbulence at the outlets and applied using time varying map fixed value boundary condition in the subsequent SIP geometry. CFD results in the study were compared to reported in vivo gamma scintigraphy deposition data for multi-dose nebulizer dry powder inhaler. The authors measured DPI deposition at different flow rates, and we have chosen the highest flow rate case with a measured peak inspiratory flow rate of 99 liters per minute. One of the main issues in comparing 2D data from gamma scintigraphy with 3D SIP model is the correct mapping between them, as the lungs are divided into central, intermediate, and peripheral pathways with gamma scintigraphy calculations. We have used Schroeter and Co. method to translate CFD branch average deposition to deposition from gamma scintigraphy calculations. This table shows how the central, intermediate, and peripheral depositions can be calculated from bifurcation average deposition data. We have generated polyhedral meshes for upper TB airway and SIP models using fluent measure. To capture the strong gradients in the GPI-Z, we had to use regional grading as shown in this figure. We used a transient solution for upper airways and specified a polydispersed aerosol based on in-house sizing data for nebulizer DPI at a similar flow rate to the in vivo data. SIP geometries are solved with a steady state assumption and monodispersed particle injection based on CFD data from a prior geometry. Laminar flow was assumed in B8 to B15 SIP geometry, whereas turbulence was solved for other models. This video shows particle transport and deposition in the upper airways. The spheres show deposited particles, and the point particles show all the track particles colored with local velocity magnitude. We use a square wave with a total time of 3 seconds, and the particle injection is for initial 0.5 seconds. The figure shows deposited particle colored by size in the upper as well as in the SIP geometries. The table compares regional deposition from the CFD data with the in vivo gamma scintigraphy data. Here, the intermediate and peripheral depositions are combined to be consistent with our previously published studies. Overall, CFD shows reasonable agreement with averaging the relative difference in the regional depositions, so less than 15% error. In conclusion, our current study showed reasonable agreement of complete airway model with in vivo data for nebulizer dry powder inhaler. We are currently working on implementing polydispersed aerosols for SIP airways and improving near-wall Lagrangian modeling framework in OpenFOAM. Further, we are also extending complete airway model to better capture lung physiology and to include a model for exhalation. I would like to thank NIS for funding this work, and thank you all for listening to my talk.